In nature, microalgae spiral through water, turning their bodies to chase the light they need to survive. We bring this instinct to UAVs and present aware, an adaptive whole-body active rotating framework that enhances LiDAR inertial odometry through human-in-the-loop interaction, keeping UAVs always aware of the unseen in degenerate environments. Compact UAVs are used in GPS-denied industrial environments like infrastructure inspection and disaster response. Full autonomy is often impractical, as UAVs cannot identify all mission-critical areas and hazards may disrupt pre-planned paths. Human-in-the-loop control is therefore essential. LiDAR is preferred for its robustness, but small UAVs can only carry lightweight sensors with narrow fields of view. In complex or feature-sparse settings, this limited FOV leads to odometry failure. Existing methods rely on heavy gimbals or fixed strategies, failing to balance perception with safe human control. To solve these problems, we introduce AWARE, an observability-aware control framework designed for high-fidelity LiDAR SLAM and human-in-the-loop interaction. Inspired by the spiral swimming of microalgae, AWARE actively rotates the UAV to continuously find the optimal viewing angle. To achieve this, we developed a differentiable observability-aware MPC that maximizes perception accuracy. But since aggressive rotation can destabilize the drone, we introduce an RL agent that continuously learns from diverse context database. It dynamically tunes the MPC weights to securely balance stability and exploration. Finally, we integrate safe flight corridors with human-in-the-loop control, ensuring absolute safety while preserving the pilot's intent for complex surveying tasks. Instead of synthetic data, our high-fidelity simulator uses real-world point clouds to expose drones to actual physical geometries. By imitating expert human baselines, our reinforcement learning agent dynamically adapts its flight controls. This real-to-sim-to-real approach accelerates training and guarantees a seamless transition to real-world deployment. First, passive fixed-rate scanning lacks environmental awareness, blinding the drone to feature-rich geometries and causing severe drift. Second, static optimization-based MPC relies on fixed algorithmic weights. Since it cannot adapt to structural changes, localization accuracy inevitably degrades. In contrast, AWARE continuously perceives its dynamic surroundings. By dynamically adjusting control parameters based on real-time state and environmental context, it actively maximizes information gain. As a result, AWARE consistently tracks stable geometric features, achieving significantly higher localization accuracy than all baseline methods. Quantitatively, it attains an average AP of 3.41 meters, reducing error by 27.8% compared to the best static MPC baseline, 4.72 meters, and by up to 84.9% relative to passive fixed-rate scanning. To assess the real-world performance of AWARE, we further deployed it in previously unseen environments. Before each flight, we built a high-resolution prior map using a survey-grade LiDAR scanner, and used it for precise scan-to-map registration to recover ground truth poses. We evaluated AWARE in 4 challenging scenes, including an underground tunnel, an abandoned athletic facility, a derelict bunker, and a dense forest. Across these diverse environments, AWARE maintained reliable localization with centimeter-level accuracy in most scenes. For example, it achieved an AP RMSE of 3.55 centimeters in the dense forest, while still keeping the error bounded in the 400-meter underground tunnel, where the AP RMSE was 1.35 meters. This trend is highly consistent with the simulation results, demonstrating strong sim-to-real transferability. Thanks for watching.